as Dr. mentioned, is that I like to teach. I've been teaching now for 24 years now at Penn State. I still enjoy teaching a lot. I think it's great to interact with young people, learn from the young minds, and enrich our life. All right. I'm going to talk about the entropy. As you can see, the title is very short. It's entropy, just one word. I understand everybody knows what entropy is, but I want to give a perspective about the history of thermodynamics. As you know, that there's one milestone in thermodynamics. That was back 150 years ago when Gibbs is the greatest American scientist who combined the first and second law of thermodynamics and developed the combined law. And that combined law was developed again 150 years ago, 1870s. It's about the classical thermodynamics, and it's for equilibrium system only. The reason is because Gibbs was interested in studying equilibrium system at that time. However, he realized that some years later, systems are not at equilibrium, right? So at least you have this statistical fluctuations in the system. And then he developed this statistical mechanics, actually coined the term called statistical mechanics. His paper was published in 1901, 30 years later, after his combined law. And he takes all studies in the previous centuries, and they developed two very fundamentally important laws for us. And we have been using thermodynamics a lot, but however, statistical mechanics is kind of largely left out for what we typically learn. As you will see today, that's a very, very important component we should not forget. And then about 20 years later, and the quantum mechanics was developed, was invented. You can think about, of course, again, based on a lot of research before the 1920s. And then because of this quantum mechanics was developed, and then statistical mechanics was further developed from the classical one to the quantum statistical mechanics about 20 years later. And however, those theories cannot be directly used. And it's until the density functional theory was discovered or invented in the 1960s. And the reason is because the systems are too complex. Okay. And this density functional theory is kind of simplified these complex systems and made it very approachable. However, the calculation was still very, very complex. It took many years until 1980s. We can do some real calculations. Well, you can see 1960 people do some calculations too, but 1980s is what it really is a breakthrough and get density function theoretism. At the same time, we know that Gibbs was for equilibrium systems, thermodynamics for equilibrium systems. However, we know this is not at equilibrium. In addition to statistics, there will be irreversible thermodynamics. Again, it has been developed from the beginning of the thermodynamics, and however, it was very nicely formulated by Ansarg and Prigogine in the 1930s and the 50s, and then was thermodynamic modeling, and then the internal process by Mashill in the 1980s. So I learned a lot from Kaufman, and I was in Mashill's classroom, so I learned a lot from them. Looking back, recently I found that actually Ansarg needs to be revised, okay? So make it more useful. I'm going to mention that in just one slide at the end of the slide lecture today, but if you want to learn more, we can discuss that one in the future. Okay, entropy. So what is entropy? I'm sure that everybody has some concept, but you keep that question in your mind. Then why is it important that we know it? And then understand how to measure it. Well, that Dr. Gore is expert on that one. Because he has one of the best facilities in the world to measure entropy. Okay. And then how to predict it, right? We can measure it, but how can we predict it? From the scientific point of view, we want to understand it, we want to predict it. Okay. And as you can see, both Dr. Guan and I come from China. So when this is a calligraphy in Chinese, this is how it's written in the standard Chinese. But if you write it in the artistic way, it looks like this. This has two parts, this word, okay? The left side is fire. The right side is negotiation. So what it means is that if you study entropy, you negotiate with the fire. That's pretty interesting, I thought. I don't know who invented this word, in Chinese, but it's really a figure in speech, right? If this, you negotiate with the fire, okay? So of course we know the second entropy is important because the second law of thermodynamics, it says everything, every process in the universe produces entropy. If it happens, it must produce entropy. And for example, I was a sabbatical at Cambridge last year, and I was staying in the same college as Steve Hawkins stayed for 52 years. And he has a very interesting book about black holes and talk about entropy of black hole. And also, if you want to learn how entropy can be applied for life, this is a very interesting book. It's both a bestseller. This is international bestseller. This is New York bestseller. It's got the order of time. It's got physics has found it. It's potent. That's entropy. Okay. All right. So where did entropy come from? Well, it's to the Industrial Revolution. It's in the 1760s. Started about 60, 80 years. One of the signature of this Industrial Revolution is this iron production. Okay, if you have visited UK, you may have seen this bridge. This bridge is a photo I took last July 2022 in UK, in a city, not a city anyway, it's a village, about 1 hour driving from Birmingham. So this is the first iron bridge in the world. It was constructed in 1779. You see that around 1760, as the Industrial Revolution started, and the UK was the leading country to do this one. They have erected this iron bridge. It's still functioning. I guess still functioning. That's 100 years before Gibbs did the combined law. Okay, Gibbs did 1873, right? That's about 100 years old. There's a lot of blast furnaces there, still older ones. Okay? It's beautiful. It's still there after 250 years. And as you know that the clashes, you look at the time, right? 1822 compared to this time here, right? This is about at the end of the Industrial Revolution. He was born. Then he started this one, of course, with many scientists. He invented entropy, but he did not invent entropy itself. He said entropy change. He said, boy, with this engine, right? Because this locomotive engines, and he said, people find some problem. You cannot put all the heat into the engine to do the work. Some heat is lost. Yeah. So what heat is lost? And then people develop this kind of cycle, and they define the quantity, which classically defined called the entropy change of a system, is equal to heat put in or take it out divided by temperature. Okay, this is for the reversible system, equilibrium system. And of course, then a Boltzmann is born in 1944. You can see here 1844. Sorry, so he's 22 years younger than Clausius. And then this is a graveyard in Austria, Vienna. And you see that actually this was not an original place he was buried, but it was moved there by the government. They're going to put all the famous people in the same place. As I visited there, was 2014, that was 8 years ago. And this is S equal to K log omega, right? Okay, so that's a very famous equation about entropy. See, this is entropy change, this is total entropy. Okay. Is the K Boltzmann constant times log W. W is the number of configurations. And then, Gibbs always is very creative. He's the greatest scientist based on Einstein. And so when he made the combined law, he said, okay, he derived that equation. He says the internal energy of a system is a function of entropy and volume. And then I mentioned Clausius and Boltzmann. There's another great scientist that was the first professor at the Cavendish lab in Cambridge University. His name is Maxwell. So Maxwell, he read his paper Then he found this is extremely interesting, right? Because now it connects the entropy to the internal energy. Okay, so then he made two models by himself, with his own hands. And I knew that there was one at Yale University because he sent one of them. He sent his model to Gibbs in 1875, I believe, or 74. I knew there was, but I didn't know when I gave a talk at the Cavendish last year. It turned out they told me one person, oh no, we have another one here. So this is actually one, which Maxwell turned out he made it two. He sent one to Cambridge, to Yale University. Gibbs was a professor there. He kept one himself at the Cavendish lab, 1870s. Okay, 150 years later, this model is still there. Okay, same model, and have this it's a text to describe what it is. Basically, these are the lines that he drew, and this is a two-dimensional line projection there. It's fantastic. That's just unbelievable. Okay. And then Gibbs this entropy, right? So it's equal to KB, PI log PI. So this equation is different from the Boltzmann equation. Okay. So you see, he was a similar age. Okay. Similar age as the Boltzmann. Boltzmann's 44, right? He's 1839. He's a bit older than Boltzmann. So he went to Europe. Gibbs went to Europe, moved around, and learned all this first law, second law from the people in Europe. He came back, derived this combined law. Okay, and then he derived this. We call it Gibbs entropy. This is PK log PK, PI log PI. What it means is PI log PI are the probability of different configurations. And then, as I mentioned, that Stephen Hawking, and he's 100 years younger than Boltzmann and Gibbs. He talked about the black hole of thermodynamics. He passed away 2018, and then in his the college, he made a plaque for him on the ground out of his office. Stephen Hawking. It says, "Remember to look up at the stars and not down at your feet." But of course, you have to look down your feet to see this equation, the entropy equation. You see, this entropy equation is different from what the Gibbs equation, right? Gibbs has log here, okay? And Boltzmann has log too. But the Stephen equation, and actually not his equation, is the Bekenstein's equation. Has no log scale. That made me think too. All right. But then we talk about entropy change, right? We talk about the equilibrium, the system, closed system, okay? Closed equilibrium system. So if this is not closed, you have to add another entropy term, right? We know this is called a partial entropy of a component I. Okay. So this is equilibrium open system. That means system is surroundings, it changes the heat and the mass continuously. But if the system is not in equilibrium, still open, right? Change heat, open, and non-equilibrium. We have to add another thing because another term. Because any internal process will produce entropy. We know that already. Okay. So if you do that one, then we have three terms now. So that's what we do not teach. We usually teach this one. We even don't teach this one. Okay. Well, of course, nobody teaches this one. Okay. So not in textbook. I mean, some people teach, but not in textbook. Okay. Turned out these two equations are in Masahila's book. That's the only book I saw had these two equations. Okay. But this is very significant. Why? Because dq is what goes back to the first law. We all know that. If you take a dq, right, left side, you got three terms on this side. You put it into the combined law, you got this equation here. Now it means that this mu I, chemical potential, actually has entropy into it. That's extremely significant because it's far less recognized, that one. Okay, then it gives equilibrium is at the last term equal to 0. Okay. And if it's not equilibrium, we will have the irreversible process, which gives this term must be positive. And the internal system could be, any system can have many internal processes. Each of them must be positive if that happens. Okay, then we get free energy, Helmholtz and Gibbs energy all come from this equation. Okay, there are more questions. Is that how can second law explain the formation of ordered structures? Right, that's a very interesting question. People asking, and actually because religion field, many people discuss it, how the second law can support the God or against God. Okay, that's very interesting. And then the question is, what is the total entropy? For example, in this classroom, you guys sitting there, what's the total entropy of the class, right? And how can be both melting and solidification process, right? Increase entropy. That's interesting because we can melt stuff, we can solidify, right? Both are increase entropy. Then how about total entropy of the universe? That's even more bigger problem. Oh, about the entropy of black holes. Okay, but I do want to first, before I start out about Einstein as some people say he didn't say that. Okay, but anyway, and he's 1879, right? 1879, so he's 30 years younger than Gibbs, and he is famous, but it was the God does not play dice with the universe. That's because it's about the quantum mechanics. Okay, quantum mechanics is uncertain. Okay, it's uncertain. It's probability. It's not like a given deterministic. It's probability. Okay, and it's stochastic was deterministic. And that's very interesting two things, right? Can the system both be stochastic and deterministic? Or they must be, right? We know that because we have statistical mechanics. Then we have no system entropy increase. How could this be reconciled together? That's pretty interesting. But then my question is that if God does play dice, what dice would it be used? And how it will be played? Okay. So it's really statistical mechanics by Gibbs. Okay. Actually, Gibbs already answered this question. Gibbs said we should imagine a great number of systems of the same nature, but different configuration and velocity. That means we have a big system, but we can imagine this system can be organized in different ways, okay, with same nature, but different configurations. So that's the dice we have. That means the multi-phase dice. Then we put them together, embrace all of them, okay, combination of all these subsystems. That's how you play them, right? And then when you do the experiments to measure it, you actually do statistical inquiries into the condition and with respect to the configuration and find out if the average them together in a certain time, how the system behave. It actually keeps answering his question before Einstein really even asked it for it. Okay, this is the God, okay, and this is the place, this is the dice. Okay, this is the universe. So the God plays the dice with the universe. That's the text here is all from Gibbs's paper in 1901. I just highlighted it. Okay. The question then is very important. How do you define or select the configurations? I'm going to play a movie here, not a movie, the YouTube here, called Emergent cage Thaumatrope configurations. So this is the piece of paper. On one side, you have the bird, the cage, right? If you move to another side, you have the bird. Okay, you see I have a bird, right? I hope you hear the music too. Do you hear the music?
Okay. Yes, we do.
All right. So if you spin slowly, you see bird, cage. You spin fast, you see bird on the cage. It's a cage. Bird, cage, bird, cage. Then put it in the cage, right? Okay. The question to you is that, is the bird cage separately correct, or bird in the cage correct? Okay. Of course, you say both are correct, right? If you fast enough, you see bird on the cage separately. If you see very slowly, if you react very slowly, you will see a bird in the cage. So both are correct. Depends on your resolution. Okay, so that makes it very difficult now. But anyway, we have statistical mechanics. What it means that we have a lot of different configurations. Each has a probability. In this case, we have half probability. Right? Then we can calculate entropy. Entropy, we have two of them, just log 2. Basically, entropy equals log 2. KB log 2, right? Okay, so we know the entropy of the system. But remember that, as I mentioned, all the configurations are the same size, right? Same size, same temperature, same volume, it's the same. However, if each configuration, that's what happens. So you got this Gibbs statistical mechanics, you got a partition function, you got a probability, you got a free energy, you got entropy, and then you find that for a system with one configuration, that's only pk equal to 1, then f equal to ek, right? Because this one equal to 0, you only have 1 times ek, that's the probability you have. And then you find, however, we know the definition F equals E minus Ts. If you want to make the two equations identical, S must be equal to Sk must be equal to 0, right? That means all the configurations must have zero entropy itself. So that's good. That's okay. So what it means is that each configuration is called a pure quantum configuration. That means it only has one configuration, each of them. But however, in the reality, in the real world, we have a systems is not a pure quantum state. Of course, you can always go down to pure quantum state, but there's too many. That's why the quantum mechanics could not be solved until DFT, density functional theory, was invented. Okay? Because too many. Then how do we solve this problem then? We can look at this one again. What it means is that each configuration is not a pure quantum state. They have entropy too, right? Then remember that we have entropy between the configurations. Then each configuration has its own entropy. Of course, just add them together. So this is from Gibbs statistical mechanics. And this means the extra term we have to add because each configuration has its own entropy. Of course, each configuration can go even further, right, to more detail, sub-configurations. Remember, all configurations must have the same MBT, or the same parameters as the system. You can go all the way down, all the way to electrons, right? That's where you can down the quantum scale. That's what DFT can tell us. So that means typically we go from top down. Okay, from the system, we divide into the configurations. We can calculate it. Most of the time, we assume this is 0. We get the first term only. But if it's not 0, you have to go down further until we find the one that goes to 0, or it never goes to 0 because we cannot solve this one. So we go down to quantum mechanics. Okay, but on the other hand, we have the tools. We can go from bottom up, right? From the bottom up, we can go to derive all the equations from the bottom up. Look at the bottom up. But if we really want to get the whole picture, we have to put them together. Okay, that's what we call Zentropy. Z is for the partition function, basically sum of all entropy from the electron level, from quantum mechanics all the way to whatever scale you measure. You can think about you measure material, you can measure a society, a forest, or measure planet, or the black holes, or the universe if we can. But I think we cannot do the universe because we cannot define the system of the universe. Okay, so what about quantum scale? As I mentioned, it's really 1960s. And Dr. Gore mentioned that I was just about the 60. I was 1 year old when this was developed. And then you can calculate the entropy or advantage of the electrons and the phonons. And then you can do the ground state. You can do the long ground state. That's very important. You can put them together, get the entropy of any configuration if it's stable. If it's not stable, of course, it doesn't exist, right? That means you don't have entropy because you cannot have entropy because you have the negative imaginary frequency. So you can only talk about the stable non-ground state. And then if you put this one together, then we have total entropy. That's where Dr. Gore and the experiment can measure. You can measure heat capacity. So we have quantum mechanics, we have statistical mechanics, we have thermodynamics from experiments. Now we believe that we can predict the entropy and can compare the prediction with the experiments. That's very important. So if you do only one part of it, right? That's it. So the community of statistical mechanics, they do this part. But the quantum mechanics, they do this part. I can see that neither part is sufficient to be in agreement with the experiment because we need both of them added together. And then we can do advantage add together. They can do prediction. We can predict the emergent behaviors. We can predict the disorder fluctuation. We can predict inharmonicity. All right, but so how can we go back to reconcile ourselves with the standard statistical mechanics then? So we know that the difference is only one term, right? Here we don't. This one is equal to 0 here. Okay, then F is also the same. Just change it from E to F because now we have S, and then this would be from E to F because we now have S. Then the probability also need to change. But it's will be the same if all the SK equals 0. That's where the standard statistical mechanics was derived on the quantum mechanics. It's all pure quantum state. So it's very nice when we realize this actually not in contradiction with the standard statistical mechanics. And then how do we predict the emergent behavior then? Emergent behavior means that like the bird and the cage, right? You have bird and a cage. You put them together, they show the bird in the cage. So that means that behavior, bird in the cage, is not represented by bird and the cage separately. Okay. For example, there are two cases I want to show here. One is the water, right? So water, the volume, this is like the volume, specific volume, when temperature decreases, and it's going to decrease, but then at some temperature decide, no, I'm going to increase, right? So the volume is going to increase, the temperature decrease. That's why in the winter you have to let all the water out in your pipe. Otherwise, it gets broken because of volume expansion. And the same thing for the organic materials, like this iron strip platinum in my alloy, same thing. You see, you have some expansion is going to positive become negative, and then become positive again. Okay, this is called emergent behavior because it's not what you anticipate from the system. Okay, so but those kind of discoveries are by chance, right? By accident, a serendipitous discovery. Can it be predicted? Okay, so I will show one case this time because we don't have much time. So it's for the iron strip platinum. So iron strip platinum, we know the iron is spin, has magnetic spin. So you have ferromagnetic spin. You have spin flipping, right? This spin can change directions. Okay, so if you have depends how many ions you have. Iron atoms you have, you can say you take 9 of them, you take the Cornelius spin configuration, you get 512 of them. But if you build symmetry, you only have 37 are unique. Okay, then you calculate all the energy from DFT at 0 Kelvin. You can calculate all the free energy. If you know thermodynamics, you can see that at any temperature, the ground state is always stable. That means from thermodynamics point of view alone, from energy point of view alone, there'll be no transition. But we know that's not true because we have magnetic transition. It's because of competition between this one. Okay, so you can calculate the probability use the Zentropy theory at 0 Kelvin, 100% is ground state, and but the temperature increases, okay, around the 200 degree, and here you start to see the transition. Okay, the decrease of the probability of the stable configuration because you don't have one, but you have 510 of other ones. Okay, so much more than that. And then at some temperature, which is I believe is 275 or 300, I should put temperature here. And then this one becomes less than 50%, even though it still has lowest energy. But we can calculate the magnetization. We can calculate the phase diagram, temperature pressure phase diagram. Even more important, we can do the temperature volume phase diagram. So each line here is a fixed pressure. This is the ambient pressure. The volume is going to increase first, and temperature goes up, and then start to decrease, then go increase again. So it is a purple area. You have a negative thermal expansion. It's because the metastable configurations, they have a smaller volume. Everybody has a positive thermal expansion, but because smaller volume replace bigger volumes, and the total volume may decrease. That's called emergent behavior. Everybody has a positive volume increase with temperature, but put them together, they have negative volume increase with temperature in this range. At the critical point, the volume change becomes infinite, negative. That's a derivative of this curve. And in that case, I do have another example. It's ferroelectric polarization. Let's tighten it. You know that the low temperature, this is a lattice parameter as function of temperature. It's a CA ratio, you get tetragonal. And you go temperature high enough, it becomes cubic. You measure the lattice parameter by X-ray. So if you think about the bird in the cage, you have the bird, you have the bird in the cage, you have the bird and the cage separated, then the bird in the cage, right? Could be very similar to that. So you have the polarization, you have the tetragonal, you have displacement, then you increase temperature, it becomes cubic when you do the experiments. But remember, atoms are not static because they change, they move all the time. And then we can do experiments too. People find that if you look at the titanium atom, which is in the center here, it actually always displaced. You always see a ratio, even above the macroscopic cubic. you still have the titanium tetragonal displaced. It's C and A, even way above that temperature. And also polarization as the atom is displaced by this XAFS experiments. But for by X-ray and a neutron, it's a cubic, no polarization, cubic. So which one's right? Okay, now I think both are right? X-ray has a lower resolution. This XAFS has a high resolution. Okay, high resolution see more details, and the low resolution sees the average. So we can do the empty simulation. You can see you have this cubic, but individual titanium atom is moving all the time. You can measure the individual motion of the titanium. You can see it goes this way, then goes that way, then goes that way. It changes directions all the time. If you decrease temperature, it changes less frequently. You see this blue, this free atom, the green one is like this distance, right? But this one is much longer. It stays much longer there, so it doesn't change that often. If you go to 0 Kelvin, doesn't change anymore. So it's really kind of the bird in the cage. You have all the bird, okay, and then bird and the cage separate, but when you get high temperature, they mix each other. So then you can do the prediction. The red line is our prediction because we use the experimental measure lattice parameter. The beginning is like all cubic tetragonal, and it becomes cubic by experiment. But I look at the individual atoms, it's still tetragonal. Okay, also has a polarization too. This agrees perfectly with the high resolution experiments. All right. So what happens is that we only have actually 3 configurations. One is the tetragonal with polarization. Another 2 are the tetragonal with the domain wall. One goes this, one goes like that. And then 180 domain, one go up, one go down. Okay. So you get the only 3 type of configurations. And people calculate the energy. So this is the first one. This is 180 degree and 90 degree. The main one put together, we actually don't predict it. When predict transition, it's remarkably agree with experiments, only 13 degree off. And this is also use 0 Kelvin energy only. If we had entropy that we're working on now, we expect it to be even closer with the experiment. Okay, so we are applying to many different topics, such as multiferroelectric, which have both ferromagnetic and ferroelectric and ferroelastic. Put all 3 effects together, see how the system behaves. That'd be very interesting. We're also trying to predict whether we're trying to use our theory, whether we can predict superconductors, right? We know that today we have a low temperature superconductor can be explained by BCS theory. High temperature superconductor has no theory. We think maybe the Zentropy theory can put them together. As I mentioned that I was in Cambridge, so I like to do the entropy of black holes because that entropy equation has no logarithmic. So I want to see how these 2 can be combined together. We have some papers, preliminary ones on this archive, which hopefully will be accepted for publication very soon. How about this one? So the bottom line is that with this kind of theory, you can predict the energy landscape, okay? From the quantum, statistical, and they can predict the experiment, agree with the experiment. So we can predict the apex, predict the valleys, okay? Then we know that the phase transition or any season change basically from here to there, right? So we can predict the barriers, okay? Then maybe that's very exciting. We can predict barriers, predict the instability. Then we can predict the kinetics, okay? And we look at this one. We have a new theory called the theory of direct across phenomena, which can predict the coefficient, kinetic coefficients, so the energy barriers, okay? Between the states, you have one state here, one state there, right? So you can see the barrier, basically predict the kinetic coefficient. And also we can put a second derivative in terms of the cross phenomenon, like thermoelectric, thermodiffusion, of electromechanical properties, right? Actually, all these things can be predicted. Of course, that's just in the future. We have done some work already. And if you're interested in this paper published last year, we talk about this details. All theories, okay? Basically, it's flux equation, that's the key. Okay? That's what the irreversible thermodynamics is about. So we propose this equation. We can calculate this cross phenomenon in the 3 different derivatives of the potential, which is the second derivative of the free energy. So it means if you get free energy, they can calculate all stuff, all things. Okay. Well, as you know, you are students, as Dr. Gore told me, you are the first or second year grad students, right? And you're going to change the world, okay? Because most things are creative things are done by graduate students. So I'll give you a few challenges, okay? See if you're interested to explore in your future careers. First one is that we talk about these configurations. But in the case, there are two configurations. In the Einstein platinum, we have 512. And in the titanium, we have 3. But then the question that for a very complex system, how can you make sure you get all the configurations? But often it's too many of them, right? And then subsystem, right? You know, you have to divide a subsystem. You have to talk about the interaction between subsystems. That becomes very complex. How to do that? If some of you know the renormalization group theory, it's talk about the interaction between the pairs, triplets, and the quadruplets, and to infinity. Okay, it's a very nice theory. But how can we implement it and make predictions from the theories we know? Okay. And also with the DFT calculations, right? On the quantum mechanical, we can do small size. But sometimes size is too big. So what is the size is enough? Chip size is enough, right? Configuration. In the case we showed for the lead titanate, the people used the 50 atoms. Okay. So how do we judge 50 atoms is enough? Because the domain where energy converges. So it's convergency is one. But that could be sometimes could be too big. Okay. So how can we solve that problem? That's a big problem. And particularly, I was at an APS meeting 2 weeks ago, and they talk about there's many talks about statistical application into brains, how to understand the brain works, and what the statistics can different fluctuations, and there's some fluctuation can cause us to get a disease, right? Like Alzheimer, stroke. How can we understand it? And the last week I was reviewing a proposal from European Union, about how can we use this kind of statistical mechanics to study the breast cancer. How can we prevent it? How can we have an early fluctuation or singular to show that, oh, there's a big problem now, let's do some treatment, okay, to kind of suppress that kind of fluctuation. So it's unbelievable. It's fascinating, okay? But I think that one of the potential solutions or potential solutions is really, we have to really get the artificial intelligence into consideration. We have to build a large database, and data has to be interacting with the tools we have. We're continuously evolving, like an ecosystem. We call it data ecosystem. We give a name called ocean of data, just like ocean, the organisms develop in the ocean. Then we have to do the very clever core screening. Okay, how can we, as I showed here, is that from the electrons go to atom level, right? Go to the phases level. But how go to higher level? Go to a human, right? Society. And you have to be able to build up this kind of structure, just like a neural network. So I think that's a very promising area. As of course, all of you know that machine learning, artificial intelligence is making splash in our community. And I think collaboration is the key. I know that as I mentioned, some of you are grad students, will graduate soon, maybe study your own career, study your own field, right? Collaborations will be very critical for us to continue to develop, because every person has a limitation, and we want to put everybody together to solve these big challenges. With that, I want to thank you for your attention.
All right, so question for Dr. Liu.
This might be a
Yeah, you can go first. Yeah.
Hello, Dr. Liu. Thank you so much for the lecture. I might have a philosophical question. So if the computation ability improves and we can actually predict all the thermodynamic results with computation, what do you think is the role of experimental thermodynamics then?
Okay, so that's actually a very, very good question. The reason is because the prediction has to be validated by experiments. Okay, so if you think about the history of human knowledge accumulation, before we know how to write, right? The experience is passed by oral. You talk to the next generation. That's how we do it. That's how we do this one. So it goes by generation. And then later we started with the human learned how to write. They started writing articles, writing papers, writing books, to write Bibles, right? For example, and then you pass the knowledge from generation to generation. Yeah. So that's the written knowledge, right? And then if you go one step further, we got the scientific journals. Okay, that's a huge expansion. So we can publish all the papers individually, right? That papers become the history. Like I mentioned, for example, Gibbs' paper in 1873 was read by Maxwell. Maxwell came back, so got this model. Okay, so if you look at Industry Revolution 1, 2, 3, so the first one is the steam engine. The second one is the electricity. The third one is the computation. The fourth one is digitization. Okay, so digitization, you have data from the computation, but they also have data from experiments. If the computation cannot be validated by experiments, that means we are lacking of some understanding. Without experiment pointing that one, we can never know what we don't understand. The experiment is hugely critical for complete understanding of our knowledge of the universe, so to speak.
Thank you.
Other questions? Yeah. Oh, Shadow, you have a question? You can open your mic and just ask.
Yeah, we
Yeah,
can hear you now.
No, thank you for the lecture, sir. No, I don't have any question. No, thank you, sir. I don't have any question.
Oh, okay. Yeah, I got a question for you, Dr. Liu. I mean, thank you again for this educational and also inspiring lecture. I mean, I feel like I'm just go back to a grad student again, listen to a lectures. It's very, very inspiring. So I got one question that related to your lead titanate perovskite that modeling experiment. So it just curious to me that if you have like a qubit in high temperature, which may have globally look like a qubit, right? But locally is tetragonal. And if I can, so if that is the phase A, if I can quench that phase to low temperature and without any vibration, so it will be a true qubit phase. And so that will be phase B. And so both A and B, they are qubit phase, but one is due to the vibrational to be at high temperature, look like qubit, and the other one is a true qubit. So do you think that we will have a same or different Gibbs functions to describe them, or whether those transitions will involve any first or second order transition?
Okay, if you quench down a high temperature cubic phase, suppose you can quench so fast, right? Freeze everything, and then you go to 0 Kelvin. Then you look at the structure. Overall is cubic, but internally is tetragonal, right? So it's like one snapshot at high temperature. So high temperature measurement would average everything. But then when you use the 0 Kelvin to that configuration, you not average everything. So your free energy will not be the same.
So in that case, there should be a real qubit phase that also in the same composition, which is both locally qubit and globally qubit, right? Which is different.
Doesn't exist.
Doesn't exist. Oh, okay.
Doesn't exist.
Okay.
So if you're frozen fast enough, that means you have be faster than phonon vibration. Okay. So that will not go to next configuration. So there will be most of them would be a tetragonal position. But some of them which in the process to get in tetragonal position. So some atom will be in the cubic position, titanium.
Right.
Some of them, because in the process, but it'll be very, very few of them.
Right. So you probably know there's the XRD describe the global symmetry, right? So if we use the XRD structure to describe this phase, that will induce as you predict from your theory, will be induce some discrepancy between what the materials really are versus from the global symmetries, right?
That's right. That's right. Exactly.
Yeah.
But the importance is that at a high temperature, because you want to, the purpose of the structure is for the application, right? So that means a high temperature, the overall behavior is like cubic.
Yeah.
So that the system responds to the surrounding like cubic. Because it's all those different tetrahedral interaction combined together is like cubic. So the cubic is very useful, even though it doesn't represent the atomic configurations. But all the atomic atoms together is like cubic. So both are very important.
I see. Yeah.
Yeah.
No, this is because I mean, all of the students, they're working on different characterization. They work on X-ray absorption, X-ray XRD, and also calorimetry. We all probe different things in different time scale and also the space scales.
That's right.
So it's some different perspective, as exactly as the bird case example you see. So very fascinating. Yeah, other questions from class or in Zoom? With that, let's thank you so much again, Dr. Liu, for this excellent lectures, and thank you so much.
Thank you. Thanks everybody for listening. Okay, bye-bye.
Bye.
Thank you.
Dr.